Welcome to the deep dive. Today, we're plunging into a really critical area, one that's become, well, absolutely essential for anyone trying to make machine learning work at scale: machine learning operations, MLOps. If you're dealing with the complexities of getting models out of the research phase and into the real world, this is definitely where the rubber meets the road. Our mission today is pretty straightforward. We're taking the source material you've given us, covering MLOps concepts, the components, pipelines, the challenges, monitoring, all of it, and we're going to distill it. We want to extract the core knowledge specifically for you, our listener, because we know you're coming to this with an expert level background in ML, data science, maybe mathematics. We're assuming you've got the foundations. We're focusing on the operational side of things.
Exactly. MLOps really is that bridge, isn't it? It connects the, let's say, experimental world of model development with the hard requirements of deploying reliably in production and doing it at scale. It's about standardizing, streamlining, managing that whole life cycle. And it's inherently collaborative. You absolutely need data scientists, operations folks, business analysts, IT, all working together.
Okay. So looking across the sources, we'll hit the definition, the why behind MLOps, the life cycle phases it covers, the key components you need, how the pipelines work. The common challenges, those are always interesting, and we'll really zero in on model monitoring and then look at some real-world examples. Right, let's unpack this then. Where do we start?
Well, at its heart, MLOps is really a set of practices. It's about automating and streamlining the workflows around machine learning. The whole point is enabling large-scale, reliable production deployments. Because, let's face it, building a model in, say, a Jupyter Notebook is one thing. Running it continuously, robustly, day in, day out, that's a whole different ballgame.
And it covers the whole process, right? The sources made it clear it's not just pushing a model out the door.
Absolutely not. It spans the entire life cycle, starting way back with gathering data, analyzing it, preparing it. Then you get into model training, development, evaluation, validation, then deployment. But it doesn't stop there. Continuous monitoring and, critically, model retraining and updating. It's a loop.
A loop, not a line. Got it. So why is this so important? What's the driving force?
It really comes down to the demands of production. The sources consistently point to three main drivers: increasing efficiency, enabling scalability, and improving risk mitigation.
Efficiency, scalability, or risk mitigation. Okay, those sound good. But how do they translate into actual benefits for an organization using ML according to the material?
Okay, well, for data teams, it means getting models into production much faster. Faster time to market, that's huge. For scalability, MLOps is what lets you go from managing maybe a few models to potentially thousands. It provides the CI/CD framework for that scale. Makes the pipelines reproducible too, which is vital.
Reproducible, yeah. That seems key for consistency and debugging.
Definitely. And it helps collaboration, bringing data science, dev, and IT closer, reducing friction, speeding things up. And on the risk side, it means faster responses if regulators come knocking, or if you detect model drift. Better compliance, basically, more transparency.
And the market's noticing this need. One source mentioned some pretty dramatic growth figures: 1.1 billion USD in 2022, projected to hit 9 billion by 2029.
Yeah, that's a significant jump. It signals just how critical these practices are becoming. The sources link it to, models getting more complex, more diverse, and just the sheer need for better collaboration across teams.
Right. It's where the theory meets the practical reality of business operations.
Precisely.
So let's get into the nuts and bolts. What are the core components?
Look.
The building blocks of an MLOps system based on what the sources laid out.
Okay, the material identifies several key pieces that work together to manage that whole end-to-end life cycle. First up, and maybe the most fundamental, is data management. And this isn't just about storing data, it's the full life cycle collection, storage, processing, but crucially, versioning and lineage tracking.
Versioning data, not just code.
Exactly, ensuring quality, consistency over time. The sources mentioned ETL pipelines here, transforming raw data into usable features. That's part of it. Then you have model training and experimentation. This is where the iteration happens, but MLOps puts structure around it. Using experiment tracking tools is key. It's not just logging accuracy, it's managing all the metadata, the parameters, the code versions for potentially thousands of experiments. Helps you improve models systematically.
Makes sense.
Next, orchestration and workflow tools. These are the conductors, automating the stages, taking data, triggering training, deploying, setting up monitoring. Automation here is vital for scalability and faster time to value. Things like Airflow, Dagster, Prefect, Flight, Mage. Those were some examples mentioned.
Right, the orchestrators.
Yeah. And then, really critical, model versioning and rollback. This includes versioning the models and the specific data they were trained on.
That link seems crucial.
It is. It's fundamental for reproducibility, for debugging, collaboration, traceability, and importantly, it lets you roll back quickly if a new model causes problems in production. The sources really emphasize data versioning for this, mentioning tools like GVC or LakeFS, which offers Git-like operations for data.
Git for data, interesting.
Yeah, things like branching, merging, validation hooks. Very powerful. Then there's model deployment and serving the infrastructure and processes to get the trained model actually running and serving predictions. Often involves containers, CI/CD for automated updates. Once it's live, model monitoring in production is essential. Continuously tracking for issues like drift or decay so you can intervene proactively. We'll dig into this more later.
Okay.
And finally, underpinning it all is collaboration and governance. Setting best practices, ensuring teams work together effectively, and meeting compliance needs like GDPR or HIPAA with sensitive data.
That paints a really clear picture of the individual pieces. How do they actually come together in these automated pipelines that everyone talks about with MLOps?
Right, the pipeline is the automated flow. It's the set of processes and tools that connects all those components, taking a project from data right through to production and ongoing monitoring. The sources described a kind of maturity model, actually. 3 degrees of automation leading to MLOps pipelines. You often start with a manual process, very iterative, maybe notebook-driven, lots of manual steps.
The classic data science workflow.
Exactly. Then, stage 2 is machine learning pipeline automation. Here, you automate the training and retraining, maybe triggered by new data. Crucially, you include automated data and model validation steps. And the most mature stage is CI/CD pipeline automation. This automates the entire process, building, testing, deploying not just the model, but the data steps, the whole pipeline, enabling really rapid, reliable updates.
Okay, so different levels of automation. Did the sources talk about different types of pipelines for different jobs?
They did. They broke it down. Data pipelines focus just on the data lifecycle, ingestion, cleaning, feature engineering, getting the data right. Model pipelines concentrate on the training, evaluation, and updating workflow for the model itself. Experimental pipelines are used earlier on for rapid iteration, testing different models, tuning hyperparameters, sort of like prototyping pipelines.
Got it.
And then production pipelines, sometimes called serving pipelines. These are for deploying the trained models for live predictions.
Yeah.
And they integrate the monitoring, the retraining triggers, ongoing distribution.
And the steps within a typical production pipeline.
Generally, it follows a logical flow. Starts with data ingestion and validation, pulling data in, checking its quality right away. Then feature engineering and transformation, creating the features the model needs, maybe scaling or normalizing them. Next, model training and experiment tracking, training the algorithm, tuning it, validating it rigorously using holdback data and tracking everything. After that, continuous integration and delivery, CI/CD kicks in. Automating the build, test, packaging, and deployment of the updated model and pipeline components. Deployment and orchestration uses those tools like Airflow or Prefect to manage the rollout reliably. And finally, model monitoring and feedback loops. Continuously watching the live model's performance, checking data integrity. The feedback loop uses this monitoring data to trigger improvements, like automated retraining, with version control managing the updates. Some sources also mentioned monitoring compute resources here for cost tracking.
That sounds like a well-oiled machine when it works, but we know billing these is hard. This is where it gets really interesting. What did the source material say are the biggest hurdles organizations face trying to implement MLOps?
Oh, the sources were very clear about the challenges. It's definitely not easy. A big one, maybe surprisingly, is the lack of data science talent. Just finding enough skilled people and keeping them is a fundamental bottleneck.
The human element.
Absolutely. Then data management continues to be tough. Things like data discrepancies from different sources, ensuring ongoing quality and accuracy, and that lack of proper data versioning causing headaches down the line.
Right.
Security and compliance are major concerns. Using outdated libraries, not securing endpoints or pipelines properly, these can expose data or create vulnerabilities. Solutions mentioned involve better patching, multi-tenancy, anonymization techniques like PII hashing, maybe using edge computing.
Security is always a big one. What else?
Inefficient tools and infrastructure. ML training and testing needs powerful hardware, which can be expensive or hard to access. And sometimes teams don't use tools efficiently, like relying too much on notebooks for tasks that need scripts. Using cloud resources or virtual hardware was suggested as a mitigation. The need for iterative deployment was also framed as a challenge, or maybe a lesson learned. You can't build the whole thing at once. You need to approach it iteratively, maybe in sprints, to reduce rework.
Makes sense. Break it down.
Yeah. Another one is a suboptimal company framework. Trying to shoehorn a new Python-based ML system into an old Java framework, for example, that creates friction. The solutions are either investing in a dedicated ML stack or using containers like Docker and Kubernetes to isolate things.
Integration issues.
Yeah, exactly. And then there are the high costs. MLOps requires significant investment in tools, infrastructure, and time. Data science teams often have to fight for budget or resources. Doing solid cost-benefit analysis is key here. Other challenges mentioned were difficulties integrating ML into existing software, CI/CD, managing the infrastructure and scalability demands, the overall skill gaps in building these cross-functional teams, the change management needed to shift the culture, and constant pressure for cost optimization.
That's quite a list. It really underscores that MLOps is a socio-technical challenge, not just a tech problem. Let's zoom in on one area that comes after deployment but seems absolutely vital: monitoring. How is model monitoring defined, and why is it so uniquely critical for ML models?
Right. Model monitoring is essentially the continuous tracking, analysis, and evaluation of models once they're running live in production. And it's critical because ML models aren't static. They decay. Their performance degrades over time as the world changes. The sources pointed to several reasons why. Gradual concept drift, slow changes in data relationships, sudden concept drift, abrupt shifts, like the pandemic example changing user behavior overnight.
Right, big external shocks.
Exactly. Also, data drift changes in the input data's statistical properties. Simple data quality issues, missing values, bad formats, data pipeline bugs, even adversarial adaptation where people try to game the system, and broken upstream models feeding bad data downstream. If you don't monitor for these, your model can silently start failing.
Silently failing, that sounds tricky. What makes monitoring ML specifically harder than, say, monitoring a web application?
Several key things. First, those silent failures. A model can give you garbage predictions without throwing a single technical error code. You have to infer failure from the data or output patterns. Second, the lack of ground truth. Often, you don't know the true outcome immediately. You can't just measure accuracy in real time for many applications. So you need proxy metrics or delayed evaluation loops.
Okay, the feedback loop is slow.
Right. Third, quality is relative and variable. What's good enough performance varies wildly by use case, and even healthy models fluctuate. Setting fixed thresholds is hard. And finally, complex data testing. Checking for drift involves complex statistical comparisons between current data and a baseline, which is computationally heavier and architecturally different than checking simple system metrics like CPU load.
Okay, given those difficulties, what metrics should we be tracking, according to the sources?
The sources broke them down into logical categories. You've got your basic software system, health latency errors, resource use. Necessary, but not enough. Then critical data quality metrics. Checking for missing values, schema changes, values outside expected ranges, shifts in feature statistics, outlier detection. Basically, is the input data okay?
Makes sense. Garbage in, garbage out.
Precisely. Then the core ML model quality and relevance. This includes direct metrics if you have labels, accuracy, precision, recall for classification, MAE, RMSE for regression, NDCG for ranking, and so on. But also, crucially, monitoring performance by segment. Is the model failing for a specific group of users or type of input? And when ground truth is delayed, using heuristics or proxy metrics based on model outputs or system behavior.
Okay.
Detecting data and prediction drift is another major category. Monitoring shifts in the model's predictions, output drift, and the input feature distributions. Methods mentioned included summary statistics, statistical tests like KS tests or chi-square, distance metrics like Wasserstein, and rule-based checks, all requiring a reference dataset for comparison.
Right, you need a baseline.
Absolutely. Then bias and fairness metrics like predictive parity or equalized odds to check for discrimination. And finally, linking it all back to business KPIs. What's the ultimate impact on the business? This is often custom per application.
That covers structured data well. But what about unstructured stuff? Text, images, embeddings. That seems even harder to monitor.
It definitely adds complexity, lack of structure, difficulty getting labels, evaluating generative model output where there's no single right answer. It's tough. The approaches mentioned included things like analyzing raw data features, maybe using another model like a domain classifier to detect topic drift in text. You could also monitor text descriptors generate numerical features like text length, sentiment scores, complexity, and monitor those for drift.
Interesting. So derive structured metrics from the unstructured data.
Exactly. Or monitor the embeddings directly the vector representations. You can use distance metrics on the embeddings or even train a specific drift detection model on the embedding space itself.
And how do you implement this? Batch or real time?
Both have their place, according to the sources. Batch monitoring runs jobs periodically or on triggers. It's often simpler, more versatile, handles delayed metrics well, and allows thorough data validation. The downside is the delay in detection. Real-time or streaming monitoring computes metrics continuously. It's better for online systems needing near-instant detection, but can be more complex and costly, and might still need batch components for some metrics.
Okay, that's a really helpful dive into monitoring. So bringing everything together, the components, pipelines, challenges, monitoring what were the key best practices, and maybe some specific tools highlighted in the material for building good MLOps systems.
Yeah, several best practices came up repeatedly. Collaboration and communication is huge, getting everyone on the same page. Version control for code, models, and data is non-negotiable. Automation and CI/CD are fundamental for scale and reliability. Rigorous model validation and testing before deployment, including checks for drift robustness, robust monitoring and alerts for live models, obviously, setting up a system for continuous improvement using those feedback loops, and ensuring compliance and governance requirements are met.
Seems like a solid checklist, and specific tools mentioned.
Several examples were scattered throughout. For orchestration, Airflow, Dagster, Prefect, Flight, Mage. For version control, DVC for data and models, and LakeFS, specifically called out for scalable data versioning on lakes with those Git-like features.
Right, the Git for data tool.
Yeah. For experiment tracking, MLflow is mentioned, CI/CD and workflow, GitHub Actions, Prefect again, right? For monitoring, evidently for general ML monitoring, evidently AI and YLabs for data drift detection, and standard tools like Prometheus Grafana for system metrics and things like model age, and broader platforms like AWS SageMaker that try to integrate many of these capabilities were also noted.
Seeing the tools helps ground it. But let's talk about real-world impact. What examples did the sources give of companies actually putting MLOps into practice effectively?
There were some great examples. Starbucks, with their Deep Brew platform using MLOps for personalization, optimizing staffing, inventory, apparently led to significant revenue growth.
Oh, okay.
McDonald's used an MLOps approach for optimizing drive thrusts, product recommendations, forecasting, customer value analysis, scaled across many stores. Walmart leverages MLOps for resource management, demand forecasting, which they found beat traditional methods, fraud detection, supply chain optimization. Pretty broad application.
That makes sense for their scale.
Definitely. Netflix uses real-time monitoring heavily for their recommendation engine quality, using an internal tool called Runway to spot issues fast. Ocado, the online grocer, was highlighted for managing millions of events, daily training pipelines, and strong model governance. Lush built an end-to-end automated pipeline for an image classification feature in their app handling retraining and monitoring automatically.
Automation really shining through there.
Yeah. Revolut developed their fraud detection system Sherlock, with MLOps principles to handle massive scale and ensure liability. And Spotify went through iterations, facing challenges initially, but eventually built an end-to-end MLOps workflow that sped up model deployment significantly. These examples really show how MLOps enables companies to not just build, but effectively deploy, manage, and scale their AML efforts, driving real business value.
Those stories absolutely connect the dots. Okay, so let's summarize, pulling all this together from the source material. What's the key takeaway for you, our listener, working in this complex ML landscape?
I think the main takeaway is that building a great model, while essential, is really only the first step. MLOps provides the necessary engineering discipline and framework to ensure that model delivers value reliably and continuously in the real world. It's about managing the entire lifecycle deployment, monitoring, maintenance, updates in a robust, scalable, and efficient way.
Right. We've covered the definition, the why, the core components like data management and versioning, the pipeline automation stages and types, the many challenges organizations face from talent to tech debt. We dove deep into the critical area of monitoring, its complexities and metrics, summarized the best practices and tools mentioned, and saw how companies like Starbucks, Netflix, and Spotify are making it work in practice.
It's clearly a field that's matured rapidly out of necessity, tackling the real pain points of operationalizing AI and ML.
So here's something to think about, drawing from the sources. We see this rapid MLOps market growth, but also persistent challenges like skill gaps and integrating with legacy systems. One source mentioned a push towards open standards and maybe more unified tool chains. How do you think that trend, the push for standardization, might shape the MLOps landscape over the next few years? And what does that potential shift mean for the choices you make today about tools and strategies for your own MLOps journey? Definitely something to keep an eye on. That wraps up this deep dive into MLOps. Thanks for joining us.